Okay, let's start for final exam review. So the final examination will be comprehensive. So let's start from first topic, first order ODEs. So at the beginning of MA 2021, we dealt with first order ODE. So let's try to remember what type of first order ODEs we have studied. We look at so-called separable equations first. What do we mean a separable equation? It says the derivative of the unknown function y is a multiplication of two given functions. One is f of x, the other one is g of y. In this case, we divide both sides by the function of y, multiply both sides by dx. So we separate x from y completely. And then we integrate on both sides. Add the integral constant c to the right-hand side. This is an equation that determines y as a solution to the ODE. Sometimes it's implicit solution, sometimes we can find explicit solution. Now let's look at second type. The second type of first order ODEs is called linear equations. A linear equation can be written in this standard form. We have dy by dx plus a given function p of x times y equal to q of x. We solve this equation using so-called integrating factor technique. An integrating factor, denoted by, say, mu, can be expressed by e to the integral of p of x. This is an integrating factor. If we multiply both sides of this linear equation by the integrating factor, on the right-hand side, we'll get a derivative. What we mean is, after multiplication both sides by mu, we get derivative of mu times y on the left-hand side. Because of this reason, we can integrate on both sides to solve for mu. So mu times y, so we get mu times y equal to the integral of mu times q of x, and then plus an integral constant c. Then we solve for y. Y is 1 over mu times the integral of mu times q of x plus c over mu. Now, if we write out mu explicitly, the solution is e to negative integral of p of x. That means we flip mu to the numerator, multiply by the integral of e to integral of p of x times q of x, and then plus constant c times e to negative integral of p of x dx. And this is so-called the general solution. This is a general solution to the linear equation. We can use this expression to find any solution to initial value problems. Now let's look at the third type of equation. We consider equation in the form of m dx plus n dy equal to 0. This equation is called an exact equation. If and only if m as a function of x and y, and n as a function of y as well, satisfy the following condition. The condition says partial derivative of m with respect to y is partial derivative of n with respect to x. This is the condition for an equation to be exact. In this case, that means if we have an exact equation, then there is a function denoted by f of xy such that the derivative of f with respect to x is m, and derivative of f with respect to y is n. The general solution in this case is determined by the equation f of xy equal to na constant c. So for na constant c. Now we need to remember how to find the function capital F of x. F of x is the integral of m with respect to x plus some function of y denoted by phi of y, because derivative of f with respect to x is f. On the other hand, n is partial derivative of f with respect to y. But on the right-hand side of this equation, if we take derivative with respect to y, we get derivative of integral of m, and then with respect to y, plus phi prime. Because of this reason, phi prime as a function of y is determined by the equation n minus derivative with respect to y of the integral of m. So we can solve for phi using this equation, and then we find function capital F. So this is the technique of exact equation. Now let's look at the last type of equations we studied in this on this topic. It's called Bernoulli's equation. Bernoulli's equations. A standard expression of a Bernoulli equation is derivative of y plus p of x times y equal to q of x times y to nth power. We need to use a transformation to change this equation to a linear equation. So first, we multiply both sides by y to negative n. So we got y to negative n times dy by dx plus p of x times y to 1 minus n. The other side is q of x. From this expression, we write u be y to 1 minus n. U will be new dependent variable or unknown function. Then we see that derivative of u with respect to x is 1 minus n times y to negative n times y prime. Or that means y to negative n times y prime is 1 over 1 minus n times u prime. Then we replace y to negative n times y prime as a first term by 1 over 1 minus n times u prime plus p of x times u equal to q of x. So we get a linear equation. The standard form of this linear equation is u prime plus 1 minus n times p of x times u equal to 1 minus n times q of x. P of x and q of x are given. So we solve for u, and then we solve for y using the original definition u equal to y to 1 minus n. So these are 4 types of first order equations we have studied. Now let's do one exercise. Let's solve the following equation. On the left-hand side of the equation, we got y times log of x minus log of y plus x squared times dx. On the other side, we have 2 minus x times log of x plus x times log y dy. When we have a first-order linear equation, the first step we should take is to identify the type of equation. We need to recognize what kind of equations we have. Is it a separable equation? It doesn't look like separable. And it's not linear either. So let's check if it's an exact equation. But before we use the criterion to find whether equation is exact, we should write the equation in the standard form. That means m dx plus n dy equal to 0. So the first term is y times log x minus y times log y plus x squared dx. And then we bring the term on the right-hand side to the left-hand side. So we got quantity, say, x times log of x minus x times log of y, and then minus 2x. Let's see. Here I made a mistake. Here, this should be 2x instead of 2. So we rewrite the equation in the standard form to recognize m is y log x minus y times log y plus 2x, whereas n equal to x times log x minus x log y minus 2x. And then we compute partial derivative of m with respect to y to get log x. This is derivative of first x squared. So when we take derivative of m with respect to y, we get log x from first term. Second term has derivative negative log y minus 1. Derivative of x squared with respect to y is 0. Now let's compute derivative of n with respect to x. The first term is log x plus 1. The second term has negative log y. Last term is negative 2. If we compare derivative of m with respect to y and with derivative of n with respect to x, we realize that they are equal. Both of them equal to log x minus log y minus 1. So the second step, we need to solve for the function capital F of xy. We know that derivative of f with respect to x equal to m. So f itself must be integral of m with respect to x plus a function depending only on y. if we take derivative of m with respect to x, then we get derivative of y times log I, integral of y with respect, integral of y times log x minus y times log y plus x squared. Now, when we integrate with respect to x, y is considered as a constant. So for the first term, we keep y exactly the same and integrate log x. Do we remember what's integral of log x? It's x times log of x minus 1, right? Because we have x times quantity log x minus 1. And then subtract by integral of y times log y. We keep y log y the same, and then multiply by x, because integral of 1 is x. For the last term, we get plus x cubed over 3. And then we need to add a function of y denoted by phi of y. We know that n is same as derivative of f with respect to y. On the left-hand side, we have expression of n that's x log x minus x log y, and then minus 2x. On the right-hand side, we take derivative of f with respect to y. So the first term becomes x times log of x minus x after taking derivative with respect to y. The derivative of second term with respect to y is negative x log y, and then minus x, because derivative of log y is 1 over y. Y times 1 over y equals 1. Plus phi prime of y. Derivative of x cubed with respect to y is 0. Now, we see that x log x, we have x log x on both sides. We cancel it. We have negative 2x on both sides. We cancel them. And then we also cancel negative x times log y on both sides. Then we realize that phi prime is simply 0. So we can choose phi of y to be 0 for simplicity. Then f is this expression y times x times quantity log of x minus 1 minus xy log of y plus x cubed over 3. The general solution is determined. It's determined by the equation f of xy equal to NA constant C implicitly. It's impossible to solve for y in this case. Do we have questions?
When we integrated the 0 to get another 0, wouldn't there be a constant that we have to add to the end of f?
Right. If phi of y in general could be any constant, but on the left-hand side, if we have a constant, we bring it to the other side and absorb by the constant c, so we don't have to choose constant for phi.
So do we not have to write plus c at the end of that?
We have to write c on the right-hand side to get. This is the answer to the problem. Yeah, we have to have c on the right-hand side. Otherwise, this wouldn't be an equation.
On the right-hand side of that one?
Right-hand side of this one? Well, you could equal to c and say this is a general solution. But we would have to say this equal to c. Do we have other questions about first order ODEs? Now let's review for second order ODEs. The general form of second order ODEs we considered is a times second derivative y plus b times derivative y plus c times y equal to g of x. Here, a, b, c, and g of x are given functions of x. So this equation is also called a linear second order equation. Remember, when we classify an ODE as linear or nonlinear equation, if an equation is not linear, then it's nonlinear. There's no any other equation out of these two categories. Okay, so let's look at some general properties. We need to understand these properties to solve for second order ODE. The first property says that if y1 and y2 are linearly independent solutions to the following homogeneous equation. So we get ay double prime plus by prime plus cy equal to 0. We denote this equation by 1. Under this assumption, then the general solution to this equation denoted by 1 is any linear expressed by linear combination of y1 and y2. So we denote this general solution by yh that equals c1y1 plus c2y2 for any constants c1 and c2. So when we solve second order homogeneous ODE, we always try to find two linearly independent solutions so that we can find a general solution. Second property says that two solutions, y1 and y2, are linearly independent solutions to the given homogeneous equation denoted by 1 if and only if their Wronskian is not 0. So we need to remember the Wronskian. W equal to the 2 by 2 determinant. First row is y1, y2. Second row is derivative of y1 and y2. If we compute, we get y1 times y2 prime minus y1 prime times y2, which is not 0. This is a criterion for two solutions to be linearly independent, or equivalently, y1 over y2 is not a constant. The second criterion actually is equivalent to first one. Second one is easier to check, but if they ask us to use Wronskian, then we need to remember the definition. Now, the third property. Suppose that yp is a particular solution to the non-homogeneous equation ay double prime plus by prime plus cy equal to g of x, denoted by 2, and yh is the general solution to the corresponding homogeneous equation denoted by 1. Then the conclusion is that the general solution to the given non-homogeneous equation denoted by 2 is yg equal to yh plus yp. This is a property we use a lot to solve non-homogeneous equation. The first property, second property are related to so-called superposition principles. So we need to understand the basic properties to solve second-order ODEs. Now, let's remember some basic techniques to solve second-order ODEs. So first, let's solve homogeneous equations. Second-order homogeneous equations. First, let's deal with homogeneous equation with constant coefficients. So we have ay double prime plus by prime plus cy equal to 0, with a, b, and c as constants. So this is one case we have dealt with. We need to remember the motivation. For this kind of equation, we look for a solution of the form e to rx. Y equal to e to rx is a solution if and only if. Now we use I double f to represent if and only if r is a root of its so-called auxiliary equation. Auxiliary equation is AR squared plus BR plus C equal to 0. If we substitute e to rx into this homogeneous equation, we will derive this auxiliary equation. That's the reason we have possibly 3 cases. First case, if this auxiliary equation denoted by 3 has 2 real roots, R1 and R2. Suppose R1 is not R2, so we got 2 distinct real roots. Then the general solution in this case is a linear combination of e to r1x and e to r2x. So YH is C1 e to r1x plus C2 e to r2x, because e to r1x and e to r2x are linearly independent. So by the third property, the general solution is their linear combination. In the second case, if auxiliary equation 3 has a repeated root or a double root denoted by R, that means R1 and R2 are the same as R, then we have 2 linearly independent solutions. Y1 is e to rx, and Y2 is x e to rx. Apparently, they are linearly independent using quotient criterion. So the general solution is their linear combination. YH is C1 e to Rx plus C2 X e to Rx. For the last case, if the auxiliary equation 3 has 2 complex roots, denoted by alpha plus or minus I beta, then in this case, Y1 equal to e to alpha x cosine beta x and y2 equal to e to alpha x sine of beta x. These two are linearly independent solutions. Because of this reason, the general solution is the linear combination YH is C1 e to alpha x cosine beta x plus C2 e to alpha x times sine of beta x. We have to consider three cases because we have different expressions for general solution in these cases. That's why it's very important to start with the auxiliary equation if we have a homogeneous equation with constant coefficients. And then the next type of second order homogeneous equation is Cauchy-Euler equations. Cauchy-Euler equations have so-called function coefficients. So the general form is ax squared y double prime plus bx y prime plus cy equal to 0. Here, a, b, and c are still some given constants. The motivation to solve this kind of equation is following. We look for a solution of the form y equal to x to some power m. So x to m is a solution if and only if m is a root of the following auxiliary equation. It's am squared plus b minus a times m plus c equal to 0. The auxiliary equation of Cauchy-Euler equations is different from auxiliary equation of homogeneous equation with constant coefficients. We denote this equation by 4. So we also need to consider three cases. In the first case, if the auxiliary equation 4 has two real roots, m1 and m2, suppose they are distinct real roots, then the general solution is linear combination of x to m1 and x to m2. So we get c1 x to m1 plus c2 x to m2 as a general solution for any constants c1 and c2. For the second case, if the auxiliary equation 4 has a repeated root, denoted by m. That means when m1 and is same as m2, then we get the following two linearly independent solutions. One is x to m1. The other one is x to m times log x. These are linearly independent solutions. Because of this reason, the general solution is the linear combination of these two solutions. So we get YH that denotes the general solution is C1 x to m plus C2 x to m times log of x. For the third case, if the auxiliary equation 4 has two complex roots, denoted by m equal to alpha plus or minus I beta, then the two linearly independent solutions we look for are x to m times cosine of beta times log x. The second solution, y2, is x to, not x to m, x to alpha. X to alpha times sine of beta log of x. These are linearly independent solutions. After we get two linearly independent solutions, then we can write out the general solution. The general solution is YH is C1 times Y1, or x to alpha times cosine of beta log of x, plus C2 times y2, or x to alpha times sine of beta log x. So let's take a note here. In general, given the following nth order homogeneous equation, so we write this nth order homogeneous equation as an times nth derivative of y times an minus 1 times n minus 1's derivative of y, so on and so forth until a1y prime plus a naught y equal to 0, with constant coefficients for this general case. We still look for a solution of form e to rx. So y equal to e to rx is a solution if and only if r is a root of the auxiliary equation. So we can generalize second order homogeneous ODE with constant coefficients to any nth order ODE. So e to Rx is a solution if and only if R is the root of the auxiliary equation. We replace any case order derivative of y with R to k. So we get a polynomial an R to n plus an minus 1 R to n minus 1, so on and so forth until a1 times R plus a naught. The other side is 0. So if we solve nth order linear homogeneous ODE with constant coefficients, we still consider auxiliary equation. If we can find n distinct real roots, then the general solution is a linear combination of these n linearly independent solutions. I think you have done exercise for third order equation, right? When n equal to 3. So this is a general idea. Third order. I can't tell you. I just tell you the general case. That means we can generalize the case. Yes.
So, in the event that if we have n roots and some are real and others are complex, then how do you do the homogeneous form?
It's a good question. We have a lot of different cases for general nth order ODE, but usually in this textbook, when we have a higher order ODEs, for example, third order, fourth order, we always have real roots. We consider only real roots. For more complicated roots, we have to have some other class to consider because it's a little bit more tedious. Okay, so this is review for homogeneous equation. Now, let's think about non-homogeneous equations. So we solve second order non-homogeneous equations. Ay double prime plus by prime plus cy equal to g of x. Using third property we considered previously, we need to solve corresponding homogeneous equation and then find a particular solution. The sum of particular solution and the general solution to the homogeneous equation is a general solution to this non-homogeneous equation. So let's focus on the technique for particular solution yp. So let's consider the methods to find a particular solution. Denoted by yp. So let's remember the two methods we have used in this class. The first one is so-called undetermined coefficients. undetermined coefficients. In this case, g of x has possibly 3 different expressions. First, it's a polynomial. So we denote this polynomial by, say, bn ix to n plus bn minus 1 ix to n minus 1, so on and so forth until b1x plus b0. The second possible expression is a polynomial p of x multiplied by the exponential function e to rx. The third one is a polynomial times e to alpha x cosine beta x, or a polynomial times e to alpha x times sine of beta x, or the sum of these 2 expressions. So we got p of x times e to alpha x cosine of beta x plus q of x e to alpha x times sine of beta x. The first case is a special case of second case, because we can regard first case as p of x times e to 0x. That means when r equal to 0, we get first case. So yp, what would be yp of x? When g of x is a polynomial, yp should be a factor x to s times a polynomial of same degree, denoted by, say, an x to n plus so on and so forth until a1x plus a0. We'll talk about s later. For the second case, yp is still x to s times a polynomial of degree n, same as the degree of contained in g of x, multiplied by e to rx. So we need to consider how to find the power s. This is an extra factor. S takes 3 possible values. The first value is when r is not a root of the auxiliary equation ar squared plus br plus c equal to 0. So when we use undetermined coefficient methods, we need to make sure that for this non-homogeneous equation, a, b, c are constants. S equal to 0 in the first case, if r is not a root of the auxiliary equation. In the first case, we consider r equal to 0. So first and second case basically use same principle. We choose s to be 1 if r is a simple root. If it's a simple root of the auxiliary equation. We choose s to be 2 if r is a repeated root. If it's a repeated root of the auxiliary equation. The last case, we still need a factor x to s multiplied by the following quantity. We have a polynomial of r of x times e to alpha x cosine of beta x plus another polynomial denoted by capital T of x multiplied by e to alpha x sine of beta x. Here, s takes possibly two values. One is 0 in case alpha plus I beta is not a root of the auxiliary equation ar squared plus br plus c equal to 0. It should be 1 if alpha plus I beta is a root of the given auxiliary equation. When we have a complex root for second order quadratic equation, then the complex root must be a simple root. So when it's root, it must be a simple root. So we choose s to be 1. These are basic values for the power s. So from here, we realize that how tedious sometimes to use undetermined coefficient method, because we have a lot of coefficients in yp to determine. Now, what should be r of x and t of x? So we let m be the largest degree of the two polynomials p of x and q of x. We look at degree of p of x and q of x. They are polynomials. We choose m to be the largest degree among the degrees of p of x and q of x. Then both r of x and t of x, they should have the degree of m. Fortunately, in this course, we deal with many cases p of x, q of x are probably first degree polynomial or constants. So r of x, t of x are not too complicated. Do we have questions? Now, let's look at second method to solve for a particular solution. It's called variation of parameters. So let's see how we find particular solution using second method. Using second method, we have to have an assumption. So suppose that y1 and y2 are linearly independent solutions to the corresponding homogeneous equation ay double prime plus by prime plus cy equal to 0. This is an important assumption. Under this assumption, we develop so-called variation of parameter method to find a particular solution. Then the particular solution yp can be obtained in the following form. It's v1 times y1 plus v2 times y2. Okay, so how do we find functions v1 and v2? Here, v1 and v2 are functions they are determined by the following two equations. First equation is v1 prime times y1 plus v2 prime times y2 equal to 0. Do we remember this? Second one is v1 prime times y1 prime plus v2 prime y2 prime equal to g of x over a. Or equivalently, when we solve for v1, v2 prime, we get v1 prime is negative y2 times g of x over a times w, which is the Wronskian of y1 and y2. Whereas v2 prime is y1 g of x over a times the Wronskian of y1 and y2. So here, w is the Wronskian of y1, y2. That's why it's important for y1 and y2 to be linearly independent, because their Wronskian is not 0. Otherwise, these two equations would break down when denominator is 0. So if we integrate for on both sides to solve for v1, v2, v1 is negative integral of y2 g of x over a times the Wronskian plus some constant c1, whereas v2 is integral of y1 g of x over a times the Wronskian plus some constant c2. So the general solution to the non-homogeneous equation ay double prime plus by prime plus cy equal to g of x can be written as v1 y1 plus v2 y2 for any constants c1 and c2. If I choose c1, c2 to be any constants, then v1 y1 plus v2 y2 represents the general solution to the non-homogeneous ODE itself. But if we fix c1 and c2, usually we would choose c1 and c2 to be 0. This is just convention. then we obtain the particular solution yp, so which is negative y1 times v1, which is what v1 times y1 here. v1 is negative integral of y2 g of x over a times the Wronski plus y2 times the integral of y1 g of x over a times the Wronski. So when we fix C1, C2, usually we choose them to be 0, so we get this particular solution. But if we let C1, C2 be arbitrary, then this will be the general solution. Yes?
Don't we also have to add homogeneous parts to the general solution?
Right. So if you look at expression of V1, V2, if we multiply V1 by Y1, in general, we would get negative Y1 times integral of Y2 g of x over a times Wronski plus C1 Y1, right? And then V2 Y2 is Y2 times integral of y1 g of x over a times the Wronski plus c2 y2. Now, if we add them up, we would get yp plus c1 y1 plus c2 y2. So we don't have to add c1 y1 plus c2 y2 again, because we already include this part as YH. So it's good observation. Okay, is there any question?
So, up there then, is y particular v1 y1 plus v2 y2? Or is that y, is that the general? No,
Right, so this is the general solution.
And then up there is the general solution too?
Um,
Or is that particular?
right, so when we fix C1, C2, we would get a particular solution. The motivation at the beginning for particular solution would be V1, Y1 plus V2, Y2. But after we solve for V1, V2, we realize that we can also include all solutions if we keep C1, C2 as arbitrary. Okay, now let's do some exercise. Let's solve the following non-homogeneous equation. We get y double prime minus 4y prime plus 5y equal to x times e to negative x. Oh, sorry. Negative 5 plus 1. Right, x times e to negative x. Okay. Now, we need to use basic property for this non-homogeneous equation. Regardless using undetermined coefficient or variation of parameter method, the first step is to solve the corresponding homogeneous equation. So we get y double prime minus 4y prime plus 5y equal to 0. This is a homogeneous equation with constant coefficients. So we write out the auxiliary equation. Which is r squared minus 4r plus 5 equal to 0. Now, if we solve for r, we get r equal to 4 plus or minus 4 squared or 16 minus 20 divided by 2. So under square root, we get a negative value, negative 4. Square root of negative 4 is I times 2. So we divide each term in numerator by denominator 2. So we get 2 plus or minus I. So in this case, if we look at general form alpha plus or minus I beta, alpha equal to 2, beta equal to 1. So in this case, we get y1 equal to e to 2x cosine of x, y2 equal to e to 2x sine of beta x as two linearly independent solutions. So they are linearly independent solutions. Then in the first step, YH is C1Y1 plus C2Y2, or C1 e to 2x cosine x plus G2 e to 2x sine of beta x. Now, second step, we need to choose a method to find a particular solution. Now, the question is, which method should we choose? Should we choose variation of parameter method, or should we choose so-called undetermined coefficient method?
Over there, is it not just sine x, not sine beta x? Because there's a beta in there.
Beta equal to 1.
Yeah, so it's there.
Oh, beta equal to 1, right. You're right, beta equal to 1. So let's talk about which method we should choose. If we use so-called undetermined coefficient method, then yp should be x to some power s times the polynomial with same degree as x, so which should be ax plus b multiplied by e to negative x. This s is chosen depending on the coefficient of x in this exponent, which is negative 1. Negative 1 is not a root of the auxiliary equation, say, denoted by 5. It's not a root of 5. Then s should be chosen to be 0. So yp is ax plus b times e to negative x. So we have two coefficients to determine. But if we want to substitute yp for a solution into that non-homogeneous equation, we need to take first and second derivative of yp. Taking derivatives sometimes could be tedious. So let's quickly determine if so-called variation of parameter method is easier or not.
Why did we pick r is equal to -1?
R is the coefficient of x, right?
Yeah.
Remember, when g of x is a polynomial times an exponential function, right? We need to recognize the coefficient of x. So before we choose a method, let's evaluate the Wronskian. So let's see what happened to Wronskian in denominator and see if integral is better than taking derivative of yp and then find coefficients. So we got y1 times y2 prime. If we take derivative of y2 using so-called power rule, we get product rule, we got 2e to 2x sine of x plus e to 2x cosine of x plus y2 minus y1 prime, which is 2e to 2x times cosine of x minus e to 2x times sine of x times y2. This is Wronskian. Remember, y2 is e to 2x times sine of x, whereas y1 is e to 2x times cosine of x. Then we realize that we can cancel out some functions. We get 2 times e to 4x times sine x cosine x here. We also have 2 sine e to 4x times sine x cosine x, so we can cancel these two. And then the remaining two terms are e to 4x cosine of x squared plus e to 2x times sine of 2x sine of x squared. Using trigonometric identity, sine of x squared plus cosine x squared is 1. So if we combine them, we get e to 2x. This is the Wronskian. E to 4x, you're right. Oops. So after we evaluate the Wronskian, now if we use the formula here, V1 prime is negative y2 times g of x, which is x e to negative x over a is 1, Wronskian is e to 4x. But y2 contains not only e to 2x, but also cosine of x. So we got negative e to 2x cosine of x times x e to negative x over e to 4x. Immediately, we would not use this method, because if we integrate x times cosine x times some exponential function, it's even worse, right? So in this way, we should choose undetermined coefficient method. So in the exam, sometimes if they didn't tell you which method to use, you write out YP, the setup for YP using undetermined coefficient method. And then we compute Wronskian. And then if we substitute Wronskian into the formula for V1 or V2 and see if integral is easier or not. So we can choose the easiest way you can use to solve for particular solution. Is there any question? So let's finish the problem using undetermined coefficient method. So we take derivative of YP using product rule. YP is set up of ax plus b times e to negative x. So using product rule, we get a times e to negative x. This is derivative of ax plus b plus ax plus b times e to negative x. When we combine them, we get, here we get negative sign in front. We get negative ax plus a minus b times e to negative x. And then we use product rule to find second derivative. Then we get negative a times e to negative x minus quantity negative ax plus a minus b times e to negative x. We combine the coefficients again. So we multiply negative sign into these parentheses. So we get ax minus a plus b, and then minus another constant a. So we get negative 2a, and then times e to negative x. Now we do substitution into the equation. So we get y double prime, which is ax minus 2a plus b times e to negative x minus 4y prime. So minus 4 times quantity negative ax plus a minus b times e to negative x plus 5y. So we have 5 times quantity ax plus b times e to negative x. The other side is x e to negative x. We immediately cancel out e to negative x from each term because it's non-zero. Now let's combine coefficients, combine like terms. So we get ax negative 4 times negative ax, 5 times ax. So we get a plus 4a plus 5a times x. For the constant term, we get negative 2a plus b from second derivative. From first derivative, we get negative 4a plus 4b. For the last term, we get plus 5b. The right-hand side is is x. So the coefficient of x on the left-hand side must be 1. That means 10a equal to 1. Now, if we simplify constant term, we get negative 6a plus negative 6a plus 10b equal to 0. So 10b equal to 6a, but we have a common factor 2. If we cancel out common factor 2, divide 2 by each term, divide each term by 2, we get 5b equal to 3a, where a is 1 over 10, then b is 3 over 50. So yp then is ax, or x over 10, plus b, which is 3 over 50, multiplied by e to negative x. Now we can write out the answer to this problem. We say the general solution is yg equal to yh plus yp. If we write out yh, we can factor out e to 2x from yh, multiplied by c1 cosine of x plus c2 sine of x, and then plus the particular solution yp. I don't have space to write out, but you can write out yourself. So this is a way to solve non-homogeneous equation.
For particular, you don't have to add the homogeneous.
Right. If they say find, right. But when they say solve an equation, that means find the general solution usually. If we find initial value solution to initial value problem, then we still need to use general solution to figure out the constant C1, C2. Now, for Laplace transforms, first we need to understand definition. The Laplace transform of some given function f of t is defined to be the integral of f of t times the exponential function e to negative s times t dt, integrate with respect to t. So after integration, if we vary the parameter s, we get a new function f of s. We need to understand how to use table of integral Laplace transform, and also inverse Laplace transform. So if we take inverse Laplace transform of capital F of s, which is supposed to be a function of t, denoted by lowercase f of t. This equation is true if and only if the Laplace transform of f of t equal to capital F of s. So when we use table of Laplace transform to find inverse Laplace transform, that means we use the table from right-hand side to left-hand side because of this relation. So from here, generally, we will include finding Laplace transform of some function and find inverse Laplace transform of some function. Here, let me mention some important formula we have to deal with. This is the Laplace transform of u of t minus a times f of t minus a equal to e to negative as times f of s. Here, f of s is the Laplace transform of f of t. So suppose they ask us to find inverse Laplace transform of e to as times some given function, capital F of s. How do we deal with this problem? First, we deal with e to negative as times capital F of s. We keep e to negative as in front. Rewrite capital F of s as a Laplace transform. This is first step. This is first step. Now, if we use this formula from right to left, the right hand, this should be same as u of t minus a times f of t minus a. Then we take inverse Laplace transform on both sides. So we get inverse Laplace transform of e to negative as times capital F of s must be u of t minus a times f of t minus a. This is very important to know how to write out f of t minus a. How do we write out f of t minus a? For example, let's look at one quick example. E to negative as times, say, 1 over s squared plus 9, for example. We keep e to negative as in front and look at 1 over s squared plus 9, which can be written as 3 over 3 times s squared plus 9. The reason is that we want to use the formula that saying that Laplace transform of sine of beta t is beta over s squared plus beta squared. So this tells us 1 over s squared plus 9 must be the Laplace transform of sine of 3t divided by 3. And this would be our f of t. Then using the formula, we get Laplace transform of u of t minus a times f of t minus a. Therefore, inverse Laplace transform of e to negative as over I squared plus none must be u of t minus a times f of t minus a. Now, f is sine of 3t. We replace t with t minus a, and then over 3. Does this make sense? I know sometimes this formula could be a little bit complicated. So when we find inverse Laplace transform involved with exponential function e to negative as, we keep it in front, rewrite the rest factor as a Laplace transform. So we recognize f of t. Then the entire right-hand side is the Laplace transform of unit step function u of t minus a times f of t minus a. So if we take inverse Laplace transform, we get u of t minus a times f of t minus a. When we recognize f of t, whatever t is, we replace t with t minus a. Do we have questions? Now, the next thing we need to do is to use Laplace transform to solve ODEs with initial conditions, say using Laplace transforms. This is another thing we need to prepare. In the midterm exams, since we have limited time to solve initial value problems using Laplace transform, the equation is not complicated. But in the final exam, you should expect higher order ODE to use Laplace transform, because you have longer time to solve each problem. So please be well prepared. Do we have questions? If you don't have question, that's all for review for the first part. Professor Brady will review for second part. By the way, remember, please look at a topic so-called reduction of order. Say, given, let me write out reduction of order. You can take a look, reduction of order. So say, let y1 be a solution to the second ODE. This is homogeneous ODE. Then y2 that equals v times y1 is also a solution. Do we remember this technique where v is integral of e to negative integral of p over y1 squared? This is just a small topic. This is assumption. Suppose we know one solution to second order homogeneous ODE, then we can find second solution, which is linearly independent of y1. Yes, y1 squared. You're right.
What's this called?
Reduction of order. So you can look at textbook. We went over this topic very quickly in class, so you can just look at this formula quickly. Okay, so that's all for the first part of review. Please take a break. Professor Brady will come here to review for second part. Okay. Yeah, thank you.